Everybody, welcome back to chemistry. And so we're moving out of looking at the electron configurations of individual atoms, and we're also moving out at looking at some of the periodic properties of individual atoms. Now we're moving into chapter 10, which is talking about how atoms bind together. So one thing I want you to have a sort of a good understanding of is the two major ways that atoms combine, which you've already heard about. So one way different atoms combine is they can form an ionic bond between each other. And this happens when one atom loses an electron and it goes to another atom which gains it, and then they combine together. Now another possibility is you can have atoms bind together when those two atoms are sharing electrons amongst themselves. And so if that happens, then that kind of bond is said to be a covalent bond. So we'll be talking about some of the subtleties that determine whether atoms form an ionic bond or a covalent bond in a minute. But one thing I sort of need to go over is, as you may be already aware, you should know that the electrons in an atom that are involved in bonding are the ones in the highest energy level. Those electrons would be the valence electrons. And it's the number of valence electrons that an atom has which determines the number and kind of different atoms it can bind. So one thing you're going to have to be comfortable with is counting the number of valence electrons in an atom. So the way we did that before is we wrote out an electron configuration for an atom and just noted the number of electrons in the highest energy level, and that was the valence electrons. But we want to do it in a faster way. We want to be able to look at a periodic table and determine rapidly how many valence electrons that atom has. So that's what I'm going to do right now. I'm going to go over here to the computer and show you how we might go about doing that. So is it possible to look at the position that an element has in the periodic table and figure out how many valence electrons it has? And the answer is yes. And so I want to show you how to do that. Let's say that your element that you're examining is in group 1. How many valence electrons it will have? So if it's in group 1, it's going to be one of these elements here. And elements in group 1 have one valence electron. So I'm going to draw the M-model symbol like this, with one dot. So what does that mean? Well, hydrogen has one valence electron, and it's because its highest energy level electron, there's only one of them, is going to be in the first energy level. Lithium also has one highest energy level electron, but it's going to be in the second energy level. Sodium also has one highest energy level electron, but now it's in the third energy level, and so on. Okay. Now, let's say your element is in group 2. How many valence electrons will it have? Well, it will have 2 valence electrons. So I'm going to draw the symbol like this with 2 dots. So next, what I'm going to do is I'm going to skip over the transition elements and go right to group 13. If your element is in group 13, it will have 3 valence electrons, and so you need to draw the symbol with 3 dots like this. If your element is in group 14, it has 4 valence electrons, and so you have to draw 4 dots around the symbol. If your element's in group 15, 5 valence electrons, therefore the symbol has 5 dots like this. Element is in group 16, 6 valence electrons. 6 electrons in the highest energy level, 6 dots. Now, if you have an element in group 17, which is the halogens, then it has 7 valence electrons, and therefore you need to draw 7 dots around the symbol. And then finally, if you have an element that is a noble gas and that is in group 18, it will have 8 valence electrons, and so you need 8 dots around the symbol like this. So let me give you an example. So let's say you're wondering how many valence electrons does the element phosphorus have? And so what you have to do is look up phosphorus. And you can see that phosphorus is in group 15. And because it's in group 15, that means it has 5 valence electrons. And so if you were to draw the dot symbol for that, you write P, and then you draw 5 electrons like this. And so here, this is sort of written out much better. And pretty much what you can see is that all the elements in like the first group have 1 dot. And so they will have just 1 valence electron. The next column over, again, you can look at all those elements there, And so they all have 2 dots, meaning that they have 2 valence electrons. You can go all the way down to the end to the noble gases, and there you can really see very nicely that while helium can't have any more than 2 electrons, 2 dots in its highest energy level, the other ones below it, neon, argon, krypton, xenon, and radon, they all have 8 dots. And the reason is because they have 8 electrons in their highest energy level. They have 8 valence electrons. Okay, so moving on. One thing you need to sort of be aware of is some of the details of how could it be that certain atoms form ionic bonds between them and other atoms form covalent bonds. And so what I want to do to sort of explain that is go to the light board and give examples of that. So let's say we have a classic ionic compound. So here I'm going to talk about an ionic bond that is formed between sodium and chlorine. So it's going to be between sodium and chlorine. So what you'll see in a minute, or what you may already know, is that what will happen for various reasons is that sodium will lose one of its electrons. It'll completely go over to the chlorine. So here you have something called electron transfer. Now, the question is, why is that the case? Why do you have transfer of 1 electron from a sodium to a chlorine and not, say, an electron that transfers from a chlorine to a sodium, or not have electrons being shared between the sodium and chlorine? It's the first possibility. So you can sort of understand that by looking at the electron configurations of sodium and chlorine and thinking about some of the other things we've learned recently about these atoms, and in particular their ionization energies and their electron affinities. So let's first look at sodium really quick. Sodium has 11 electrons, and so its configuration is 1s, 2s, and then there's 2p, and then 3s. So sodium, as you probably know, looks like this. And so what you can pretty much see, if it's 11 electrons, the first and second energy level are completely filled with electrons, so that's neon's configuration here, but then we have 1 extra electron in the 3s. Now let's write out chlorine's configuration. This is 17 electrons. And so it's going to look like this. You're going to have neon's configuration of 10 electrons, and then you have the 3s and 3p that looks like this. Okay, so this is chlorine's electron configuration. And just to point out, these atoms, as I've written them, these are the neutral atoms. So the question is, why is it that it's possible under certain conditions for sodium to bind to chlorine and form an ionic bond between them? Well, there's a particular reason for that, which now you can understand. So one question to ask is, as I was kind of mentioning before, as I kind of alluded to, what you'll probably, for reasons which I'll explain, you're going to have this 1 electron in the 3s of sodium leave it and go to chlorine's configuration. One may rightfully ask, why is that the case? Or why is it not that here this single electron from chlorine leaves chlorine and goes to sodium? So there's a couple of reasons for that which you need to know about. So let's first consider, how do we get an electron to leave an atom? The way we get that is by we adding energy to it to ionize the atom. And so to remove an electron from an atom so that can go to another atom requires some ionization energy. And so typically the atoms that are favored to lose an electron are the ones where you don't need a lot of energy to release that electron so it can go to another atom. Atoms where it takes a lot of ionization energy, a tremendous amount of energy to get that electron off, they will not be favored to have those electrons leave that atom and go to another. So let's look at sodium's configuration. So one of the things you might remember is that this electron here in the 3s, it has a relatively low ionization energy, and there are good reasons for that. And one of the major reasons is it's not paired up, so it's relatively easy to pull off that electron. And also, if you pull off the electron, you can see what's left, the sodium ion, will have a noble gas configuration, so that stabilizes the ion. So this has a relatively low ionization energy. Now, again, a question that you might want to ask is, well, why doesn't this electron from chlorine leave and go to sodium? And the reason is, you can look up the ionization energy for this electron of chlorine, and what you'll find is about 3 times that of sodium. So this has a higher ionization energy. So this just takes a lot more energy to remove. Now, another consideration as to why electrons kind of move around the way they do is not only you have to think about the energy required to pull off an electron from one atom and stick it onto another, but to understand if that electron goes to that other atom, does that stabilize the atom? And it will stabilize the atom if, when the other electron binds to that other atom, the atom releases energy. If the electron adds to the atom and the atom is releasing energy into the environment, then the atom has, with that extra electron, has a lower energy. The way you evaluate whether when you add an electron to an atom, it releases energy is through something called electron affinity. And so we talked about that after we talked about ionization energy. And what you might remember is that here the neutral chlorine atom here with its 7 valence electrons, it has the highest electron affinity energy of all the atoms in the periodic table. So when you add an electron to chlorine, it will release per mole the most amount of energy of all the atoms or the different elements in the periodic table. So this has a very high electron affinity, which is very favorable. On the other hand, you can look up the electron affinity for sodium. And so if you were to manage to force an electron onto sodium's configuration, it would release some energy, but not nearly as much as chlorine would. So this has a relatively low electron affinity. So now I'm hoping you can sort of see is that the situation between ionization energies and electron affinities between these two different atoms demands that when you have these atoms get close to one another, what will happen is that you will have here the electron from sodium in the 3s configuration there, in the 3s orbital, go to chlorine there, and it will go there. And the reason why it does that is because here, this electron of sodium here has a relatively low ionization energy, much, much lower than chlorine, so it wants to transfer over this way. And additionally, chlorine has it wants that electron, it has a very high electron affinity. So now let's write out the configurations for what we have after the transfer occurs. So I'm going to draw an arrow here and then I'm going to rewrite what we have now. So sodium is going to lose an electron. So now it has 10 electrons. And so you're going to have 1s, 2s, and then you have 2p. And then I'll put it in the 3s orbital even though it's empty. We have sodium still, which is 11 protons, but instead of having 11 electrons, it has 10 electrons. So it's missing electrons, so it will have now a positive charge. Now let's look at chlorine. Now chlorine now had 17 electrons. It's going to get one from sodium. Now it's up to 18. So we have 18 electrons. Use neon's configuration first of 10 electrons, and then we'll have 3s and then 3p. So 2 electrons here and 3s, and then here we have chlorine's 3p electrons, and then this electron here from sodium will now go here. So I better draw it green because sodium was green. So this was here, and now that goes into chlorine's configuration. And so when chlorine gets this electron, it has one extra electron from 17 to 18 electrons, and so it has an extra electron as a negative charge. So these are the configurations of the atoms after the electron transfer occur. And you can see that they're no longer atoms really, they're ions. Another thing to note is they're ions, but also look at their electron configurations that they have as atoms, or excuse me, as ions. Okay, so you have sodium's configuration here. When it's lost an electron, it's still a sodium atom, but has one less electron. So it's a sodium atom, but notice it has neon's electron configuration. So it really has a noble gas configuration at this point. So when sodium loses an electron, becomes a positively charged, it gets a very stable electron configuration. Now, how about chlorine when it picks up that extra electron from sodium? Well, you can see here that now it has a full third energy level, so it has argon's electron configuration, it has argon's noble gas configuration, so that makes that stable. So the advantage of transferring an electron from sodium to chlorine is that the ions you get in the end have stable noble gas configurations. If you think about it, if you had the transfer go the other way, that would not happen. You would not get either of them to have stable noble gas configurations. So why do these atoms now as ions bind? It's pretty simple. So let's say now we have sodium and it has a positive charge, and we have chlorine which has a negative charge, and I didn't draw these to scale. Okay, so you have two things of opposite charge, and as you know, opposite charges attract. And so basically it's on account that they now have opposite charges that they stick together. And then this area here between the ions where they stick together, this is the ionic bond. And one of the things you'll learn in a bit, ionic bonds tend to be very strong. They're hard to break. Now, there's another way that you can sort of simply write out all of what I just said, which I need to describe to you. So let's look at the Lewis dot structures of sodium and chlorine and see how they change to ions such that they can bind together to form sodium chloride. Okay, so you know that as reactants, what would be the Lewis dot structure for sodium? So you can look up here at sodium's electron configuration. You can see there's one electron on the highest energy level, which is the third energy level, so it has one dot here, right? We can look at chlorine as a reactant. It has 7 electrons in the highest energy level, so I'm going to write chlorine here and put 7 X's for its dots. Okay, so now one of the things we saw is that a requirement for these atoms to bind is they have to ionize. And the way they ionize is sodium must lose its electron here and it must go to chlorine. And so here, what the next sort of step in the process is sodium loses its valence electrons, so we can just leave Na and then have a plus here. And then chlorine has its 7 valence electrons here, plus sodium's old one. So now you can see the chloride ion now has actually 8 valence electrons. Now, using these structures, we can indicate that these ions bind together by sticking the sodium plus and just smooshing it into the chloride ion, but putting the chloride ion structure here in brackets like this. So here would be the products, and the products would look like this. We have sodium ion smooshed within brackets to chloride ion like this, and with a negative charge for chloride. And so this is just a simplified description using Lewis dot structures of how sodium becomes an ion and chloride becomes an ion, and they bind together as ions to form an ionic bond between the sodium ion and the chloride ion. Okay, so this is a great example of elements that when they stick together, one element can lose an electron to another element, they become ionized and they form ionic bonds. And as you know, this can happen between other elements, and usually it happens between elements that tend to want to completely lose electrons, which are metals like sodium, and elements that want to completely gain extra electrons like nonmetals like chlorine. So there are other examples. And so for example, you could have other examples would be like potassium iodide. Here, potassium iodide, potassium is a metal. It will want to lose an electron because it forms a stable configuration when it does. That extra electron would go to iodine, forming the iodide ion. And when you do, then it gets a stable configuration. And then the positive sodium ion will bind to the negatively charged iodine ion and form ionic bond. And so there are plenty of other examples of compounds that form ionic bonds. But what I want to do is, maybe the most important thing, is compare that to how a different kind of bond forms. And so now we're switching over. We're no longer talking about, for the moment, how ionic bonds form. We're going to talk about how covalent bonds form. So ionic bonds occur when an atom loses an electron to another, they become ions and they stick together to form an ionic bond. That does not happen in a covalent bond. So with a covalent bond, the example we're going to be looking at is diatomic chlorine. It'll be Cl2. And so here we do not have electron transfer between one chlorine and another. Instead, we have electron sharing between the two chlorine atoms. And so let me show you how that works. So if you have chlorine here, here's the first chlorine atom in the molecule. It's 17 electrons. It's going to have neons configuration of 10. And then, as you know, it's 3s and then 3p. And there will be 7 electrons in the third energy level like this. Okay, and then let's say there's another chlorine atom with 17 electrons. So one question you might ask is, well, is it possible that maybe an ionic bond can form between, say, this chlorine atom with this chlorine atom? In other words, maybe an electron leaves this top chlorine forming a positive chlorine ion, and that electron travels to this chlorine forming a negative chlorine ion, and then as ions, the two chlorine atoms stick together. Okay, that doesn't happen. And again, you can sort of understand that getting down and looking at the ionization energies of the electrons in the highest energy level. So if an electron were to leave chlorine, it would be this one here, which I'm going to point to with a red arrow. But here's the problem. As we kind of saw before, while alkali metals like sodium, their highest energy level electrons have relatively low ionization energies, halogens like chlorine have relatively high ionization energies. And so you're going to need a fair amount of energy in the environment to get that electron off chlorine and transfer it to another chlorine. So that is far less likely to happen. So instead, you do not have an electron transfer from one atom to the other. Something different happens. So the goal here of these atoms is, despite the fact that they do not have a noble gas configuration right now, is there something they can do with their electrons to achieve a basic noble gas configuration? We already said that we cannot transfer this chlorine electron to the other. The ionization energy is just too high. So what can happen is as follows. This electron here in the top chlorine, what will happen is it will leave just briefly and go to this other chlorine here and spend a time around this other chlorine, and then it'll go back to the top chlorine atom and spend time there. And basically that electron here that I'm pointing to will just spend equal time between these two chlorine atoms. This single electron here in the bottom chlorine atom will do the same thing. It will spend equal amounts of time between these two chlorine atoms. Now, how about these other chlorine electrons? Will they do the same thing? And the answer is no. So with these top chlorine electrons here, they stay localized to that top chlorine nucleus, and these lower chlorine electrons here stay localized with the lower chlorine nucleus. But these two electrons here move back and forth between the two atoms. And so to indicate that these electrons kind of move back and forth between the two atoms, we put a box here. And so that indicates that when you bond these atoms, that these two electrons here will be shared between the two atoms. Now, does this help stabilize these atoms in this molecule? And the answer is yes. And the reason is if the electron spends in the lower chlorine atom spends any amount of time in the upper chlorine atom, that's enough to fool the upper chlorine atom into thinking that it has a stable noble gas configuration. And same thing here. This electron top spends some time in the lower chlorine atom. It fools into thinking that it has a stable noble gas configuration. So when you share electrons here in the highest energy level, you fool the atoms into thinking that they have these stable noble gas configurations, and so they're stable. So to describe this process of how these chlorine atoms get together, bind and share, let me draw out some valence dot pictures here. So we have reactants, and then we'll have products over here. Okay, so we have one chlorine atom with its 7 valence electrons, which I'm going to draw as dots. Then we have another chlorine atom with its 7 valence electrons here, which I'll draw as X's. So the first question is, to get these atoms to stick together, do we have a preliminary step where we transfer one of the electrons from one of the chlorines to the other? The answer is no. Again, that does not happen. Instead, what happens is this dot here, this single dot of chlorine, which is this electron here, will be shared between these two chlorine nuclei. And this X here, this single electron here, will be shared between these two chlorine nuclei. So to indicate that, I just smooshed these atoms together to form the product, which will look like this. So we have chlorine here, and then we have the other chlorine atom here. And so they have stuck together to form a bond. So here, this pair in the middle is this pair I've boxed up here in the electron configurations. This is called a shared pair. And so you have to keep in mind, although it looks like this shared pair is sort of localized between these two nuclei, in fact, these two electrons are kind of wandering around these two chlorine atoms. Now, the other pairs here are called lone pairs. And so lone pairs are not between the nuclei of the chlorine. They're sort of on the outside on one of the other atoms, and they stay pretty localized on their territory of the atom, and they don't tend to be shared between the different chlorine atoms. Okay, so that's how a covalent bond forms. And again, the key thing here is that here, probably with the atoms, you don't have a particular atom with a very low ionization energy. And so if you have atoms with middling or high ionization energies, what they can do, though, is they can share electrons with other atoms. And when they do, then you can get equivalent noble gas configurations, and then the atoms bind together. Okay, so the next thing I want to talk about is there's something that you need to understand, sort of a basic property difference between ionic compounds and covalent compounds, which is very important.